Hello, and thanks for watching this video on bifibration of polycategories and their relation to classical linear logic. I'm Nicolas Blanco, and this is joint work with Noam Zellweger. You can find the draft paper for this talk on my website at this URL, and I will also post the slide on my website. So before going into the details of polycategories, let's first recall some context, and especially models of multiplicative linear logic. So to model intuitionistic multiplicative linear logic, we can use monadal clause category. And for classical multiplicative linear logic, we can use Star-autonomous category that were introduced by Barr, or linearly distributive category introduced by Crockett and Seeley, where a linearly distributive category with duals is equivalent to Star-autonomous category. And in both cases, the idea is that you will ask for two model structure on your category that will interpret the tensor and the pair, and a monoidal duality between those that will interpret the negation. Another way of interpreting logic in a categorical setting is by using multicategories. So multicategories have been introduced by Lambeck. So it's an analogy by Lambeck to represent sequent calculus, to interpret intuitionistic sequent calculus. So in a multicategory, instead of having morphisms that have one input and one output, you have multimaps where the domain can have many objects. And so using these multicategories to represent sequent calculus is inspired on one one hand, by the notion of multilinear map in linear algebra, and on the other hand by the intuitionistic sequent calculus. And so using this interpretation, we can define the connective by universal property instead of defining them by structure. This can be extended to classical sequent calculus by considering polycategories. This has been done and introduced by Szabo, which was who was one of Lambeck's students. And the idea is that in a polycategory, you have polymap, where now both the domain and codomain have multiple objects, and the composition is done along one object to mimic the cut rule from sequent calculus. So this makes it different from pro or props, for example, where you can compose along multiple objects at the same times. So polycategories have been used by Crockett and Seeley to model multiplicative linear logic in what they called two tensor polycategory with duals. And we can also find in the literature the terminology representable star polycategory, which is the one that we will use in this talk. And finally, I want to mention another line of work by Claudio Hermida. So at the beginning of the millennium, Hermida observed that there are a lot of analogies between multi-category theory on one hand and fibered category theory. So if you go to his nice paper there, you will see a table that recap all these analogies. And to make this rigorous, he introduced the notion of multi-categorical fibration. And it's more precisely of covariant fibration of multi-categories. We did that in 2004. And something that is quite interesting is that multi-categories that are fibered over the terminal multi-category, are in correspondence with monoidal categories. So this makes this relation precise between representable multi-category on the one hand and multi-category fibered over one on the other hand. He also used this theory of fibration of multi-categories to study the algebra for an operad, where he proved that an algebra for an operad is the same thing as a discrete fibration over this operad considered the one-object multi-category. After that, people have been interested in introduce contravariant fibration and then bifibration of multi-categories. So it has been used, for example, recently by Likata, Schulman, and Wiley to represent some logical structure. And this is closely related to the notion of fibration of closed category. So if you take a multi-category that is bifibered over one, then it is the same thing as a monadal closed category. So if your multi-category is covariantly fibered over one, you get just a monadal category. And to get closeness, you need to also ask for it to be contravariantly fibered over one. And there is an important asymmetry there, that is that the pullback, so for contravariant bifibration, has to be parameterized by a choice of input. For the push forward, you don't have to do that because you just have one object in the codomain. But in the domain, you have possibly multiple objects. So you have to choose one along which will perform this pullback. So in our paper, we have several contributions. The first is to define a notion of universal polymap that will be parameterized either by an input or by an output. And using this notion of universal polymap, we can get all the connective of MLL by saying that they are characterized by the existence of certain universal polymap. And so with this analogy in mind, we introduce star representable polycategory, which will be polycategory that has all possible universal polymap. And then we prove the following theorem, which is our first contribution, that this notion of star representable polycategory is equivalent to the notion of representable star polycategory that has been studied by Coquette, Seeley, and others to represent multiplicative linear logic. After that, we define the notion of fibration of polycategory that extends the notion of fibration of multicategory. So like in the contravariant case for multicategories, in fibration of polycategories, the notion of Cartesian polymap will be parameterized by a specific input or a specific output. And we prove that a polycategory is bifibered over one if and only if it's star representable. And so this gives a correspondence between star-autonomous category and polycategory bifibered over one. And so one of first motivation to study that was to study the structure of the star-autonomous structure on the category of finite dimensional Banach spaces and contractive map. So something that is really interesting about this category is that it's a category that comes from the category F of vector spaces, so it has a forgetful functor in it. And it is also star-autonomous, but it's not compact close, contrarily to the category of finite dimensional vector spaces. And so the two norms that you will put on your tensor project that will give you the tensor and the par are called projective and injective cross norm, and they are known in the community of functional analysis. For example, because they have this universal property that they are extremal on the set of norms that you can put on the tensor project. So if you look any norm that you can put on the tensor project and that is well behaved in some sense, will lies between those two norms. And we will see that this property of being extremal comes from the fact that they are defined using Cartesian polymaps. And finally, there is a third contribution that we won't have time to get into the details in this paper, in this talk, sorry. That is polycategorical Grothendieck correspondences. So we give a collection of different Grothendieck correspondences in the polycategorical case, where, for example, we give correspondence, so one-to-one correspondence between, on one hand, bifibration of polycategories, and on the other hand, pseudo-functors that goes into the two polycategory of multivariable adjunction. So using this fact, we recover an observation by Max Schulman that star-autonomous category of Frobenius pseudomonoid in this two polycategory. Okay, so now let's get into it. And first, define polycategories. So our polycategories will be taken to be planar, which means that they are not necessarily symmetric, basically because it's possible to define that, and symmetry doesn't really play any picture in this story. So you could take symmetric polycategories and do everything that we are doing here with only slight modification. And so we thought it was better to do the more general case. And this is in line with the work by Coquette and Seeley, where they consider linearly distributive category to be non-necessarily symmetric. And so in particular, the notion of star-autonomous category that we'll have is also non-symmetric, so it's planar star-autonomous category. And in particular, for duals, we'll have both right and left duals. So that being said, a polycategory is a structure analogous to a category. It has a collection of objects, except that it has a set of polymap from any finite list of objects to any finite list of objects. So the domain and the codomain are finite lists of objects. These lists can be empty. It should have identities, a notion of composition that are unital associative, and that have an interchange law that we'll explain later. So the fact that our polycategories are planar and not necessarily symmetric puts some restriction on the composition, but I will explain just now. By looking at how to represent polymaps graphically. So the idea is that we will represent our string diagrams that goes from left to right, and a polymap will be represented by a box that takes some inputs, so their gamma, and spit out some outputs, so deltas, so delta 1, delta 2, and A. And then we will represent composition by plugging the wire from one output of F into one input of G. So we can see there that composition happens only along one wire, one object. And so the planarity condition, which is also known as the no crossing condition, state that wires should not cross. And so in particular, it will, what it will exactly mean is that either this list or this list is empty, and either this list or this list is empty. Finally, the interchange law say that taking polymap H, and if I want to compose it with two polymaps F and G along two different inputs of H, then it shouldn't matter in which order I'm doing it. So I can start by plugging F and then G or the other way around. And of course, there is something similar for outputs. Finally, I want to give you some examples that will be important in this talk. First, there is a terminal polycategory. It has only one object and one polymap for each arity. So given two arities M and N, there is a polymap that goes from M copy of star into N copy of star. So this terminal polycategory is trivial. It's not really hard to define, but it will be really important in the theory. Then, given a linearly distributive category, as introduced by Coquette and Seeley, or if you prefer a star-autonomous category, which is a special case of linearly distributive category, you can define a polycategory where the polymap goes from the tensor product of the input into the par of the outputs. And in particular, any monadal category can be considered as a linearly distributive category, where tensor product and par are taken to be both to coincide. And for star-autonomous category, it will give the notion of compact closed category. And in this case, of course, we get a polycategory where the polymap are given by the map that goes from the tensor product of the input into the tensor product of the output. So just for information, and I'm just recalling the sequence calculus rules for multiplicative linear logic. If you're not really familiar with it, I invite you to pause the video. And using that, we'll define in a polycategory what is a tensor object. So a tensor object will be taken to be an object that comes with a binary map that goes from AB into A tensor B. So you can think of vector spaces here, and so the bilinear map that goes from two vector spaces into that tensor product. And so it should have a universal property that say that any map that has AB in the input should factor uniquely through this M, through this bilinear map. So this is the property in vector space that tensor project linearize bilinear maps. And we choose this notation because this is closely related to the rules from the second calculus. So this corresponds to the tensor left rule. So given something that has A and B in the input, I get something that has a tensor B in the input. And this M is closely related to the right rule for the tensor product. We get it by looking at the right rule and taking the special case where we have identities. And so by an identity from A, by an identity on A and an identity on B, I should get this map that goes into A tensor B. And this will induce a natural isomorphism that goes between AB and between maps that goes from AB and polymap that goes from A tensor B. So in one direction, we get this isomorphism by composing with them, and on the other direction by factorizing. So this natural isomorphism is represented by this correspondence between these two maps. We have something similar for the PAR, but where we exchange the notion of input and output. So we'll get a co-binary map, a map that goes out of the PAR into AB, but has a factorization property where this binary map is now post-composed. So everything factors through the post-composition by W. And natural isomorphism, where now we have ABs in the output and that gave A par B in the output. Finally, we can define the star in a way that is really similar to the way that it's defined in compact closed category, by saying that we want two maps that we will call the cup and the cap that has this this typing. So the cup goes from the empty list into A star, and the cap goes from A star A into the empty list. So that they satisfied what is called the snake identity. So it's called a snake identity because if you draw it, so you will get a snake like that, and taking the snake identities is yanking the snake, and so taking the snake and making it an identity. So we'll have both snake identities, and this will induce a natural isomorphism between map with A in the input and map with A star in the output. So using all this notion, we get the notion of representable star polycategory that has been defined by Coquette and Cieli, by saying that it is a polycategory that has all tensor par left and right duals. So now that we introduce that, we want to give a slightly different definition that use the notion of universality. So the idea is to get one notion or two notions, out universal and universal, that encompass all of the properties of the connective. So we'll say that a map is universal in one of its inputs or one of its outputs, if it has this kind of factorization property. So for example, U is universal if in this output, if any H that has the right kind of typing that will make it a potential composition with U will be indeed a composite. So there will be a unique way to factor H through U, sorry. And the other way around for inputs. So it's a same kind of factorization property, but now post-composing by N, by the universal map. And so in particular, if we take U to be the binary map that goes from the tensor, from A and B into the tensor product, then this will be exactly the property of the universal property of the tensor product. It will say if I have A, B in the input of a map, then I can factor it to get a map that has A tensor B in the input. Using that, we say that a polycategory is star representable if it has all universal objects. What we mean by that is that if you give me some object, some list of objects that will specify all the input and output of a map except from one, so we leave one input empty, then I can give you this input and a polymap that is universal in A. And of course, the same for outputs. So if everything is specified for the polymap, except from one input, I can find this output in a universal way, so such that it comes with a universal map. And if a polycategory is star representable, we prove that it is equivalent to the polycategory being representable star polycategory. So it's equivalent to be star representable and to have all tensor, pairs, and duals. To do that, one way is mostly by definition. So we get by definition that the tensor and the pair are universal objects. So we get them from star representability. What is maybe a little more surprising is that we can also get duals by the same the same scheme of universal property. So we get, for example, that the dual can be defined as an out universal object with respect to a cup map. And the universal property of this cup map will let us define what is the cup, and it will have built in the fact that it is a snake identity. But we could choose the other way around and say, okay, we will define duals by the in-universal property of the cup, and using this in-universal property, we can derive a cup that will have the snake equation. Also, we should note that cup and cup are also universal in A, and we can use this fact, for example, to prove that the B dual is equivalent to the object that we started with. And the other way, if you give me representable star polycategory, so something that has all tensor, pairs, and duals, I can build I can prove that it is a star representable category, so I can build any universal polymap. And how does this work? This works by, so if you give me the typing of the map except from one object, I want to derive this object and out universal map polymap in this. So the way that we do that is that we use a cup to take all the outputs and put them into inputs by starring them. And then we take all the inputs and we tensor them to get a final object. And so this object will come with this out universal polymap. We can do something similar for in universal by flipping, so exchanging input and outputs, and replacing all the tensor by pairs. And so the cup will be flipped and we gave cap instead. So this gives us a first contribution, which was to give an alternative definition of what it means for polycategories to be representable. And now we can go and define bifibration of polycategories. So first, some terminology. We'll say that we will call a functor of polycategory a poly-refinement system. This terminology is inspired by the study of a type refinement system as functor of category. And so we will draw them graphically in, in this way, vertically, where the diagram on the top will be in the domain, and the diagram on the bottom will be in the codomain, and in such a way that things that lie over another one are sent to it by the poly-refinement system. So for example, R is sent into A, phi is sent into F. And so this precise diagram is expressing the preservation of composition, because it says that a composite is sent into a composite. With this graphical representation, we can give a concise definition of Cartesian polymap, so of both in and out Cartesian polymap, which correspond to, so for the in it corresponds to Cartesian map, and the out correspond to up Cartesian map. So they are defined, for example, for out Cartesian in this way, by saying that phi is out Cartesian in this output, so it's still parameterized by one specific output. If any map that lies over a composition by the image of F will factor through F. So if it's lie over a composition, then it's a composition, basically. And the same is true for in Cartesian with respect to one specific input. So if something lies over a composition by the image of this input, so along the image of this input, then it will be a composition along this input. So something that is interesting here, and that I will come back to later, but I want to explain it graphically. It's and to give you some sense of why it works, is that if I take the base category, the base polycategory to be terminal, the terminal polycategory, then all this condition will be trivial. So everything will be trivialized on the base, and we can just forget about the base. And we see that this factorization property then becomes just the factorization property of universal map. So this explains why your polycategory that is bifibered over one is the same thing as a star representable polycategory, because then Cartesianness corresponds to universality. And in the similar vein, if the bottom diagram is a universal diagram, then the top diagram will be universal. And so we can think of Cartesian morphism to be a way to lift universality, so universal map, from the bottom polycategory into the top polycategory. Talking of lifting, we called a Cartesian lifting any map obtained like that. So given a polymap in the base, and if I have the typing of every, so if I have a refinement, if I have an object over every object of the domain and codomain of F except from one, I should be able to find one object over A in such a way that it comes with a Cartesian polymap that lies over F. And so this object that lies over A we call the pullback of sigma along F in context pi1 and pi2. We'll often just refer to it as a pullback. And the map will be called the Cartesian lifting of F. There is something, of course, similar for output, and we call the dual notion of a pullback a push forward. We'll also talk about Cartesian lifting. And so finally, a poly refinement system is called a pole fibration, or just a fibration, if it has all in Cartesian lifting. It will be called a push fibration or up fibration if it has all out Cartesian lifting, and a bifibration if both are true. So if it has all Cartesian lifting. And as I said before, a polycategory that is bifibered over one corresponds to star representable polycategory. And this is just because the notion of Cartesian map will be parameterized by some base polymap that is trivial. And so this will correspond to universal map. And in as a corollary, we get that star-autonomous are just represented by polycategories fibered over the terminal polycategory. We can use this to lift the star-autonomous structure. So as I said, if you take the Cartesian lifting of a universal polymap, you get a universal polymap. So Cartesianness is a way to lift universality, universal polymap. And so using this fact, if I have a polyrefinement system between a base category that is star representable, so it will have all universal map, and in such a way that this polyrefinement system has all Cartesian lifting of universal polymap, then the top category will be star representable. And so this is a way to lift star-autonomous structure, because we will lift all the connective by just taking the Cartesian lifting. So we can use that on the example that I mentioned before of Banach spaces. So first we can define the polycategory of finite dimensional vector spaces by just using the fact that the category of finite dimensional vector spaces is compact clause. So we get polylinear maps in the polycategory that are defined by map that goes from the tensor into the tensor. And then we can define a polycategory of finite dimensional Banach spaces and contractive polylinear map, just by defining what it means to be contractive for a polylinear map. And so this means that this equation holds that for any object A1 through AM in A1 through AM, and any linear form phi1 through phi n that goes from any B's into into the field, into a bifield. If you want to think of it, object of the duals of the bees. Then when I plug the input into F and I take, so this will give me an output that is in the tensor product of all the bees. Then I can take this output and give it to the tensor product of all the linear form. This will give me a scalar. And if this scalar is lesser or equal, or as an absolute value that is less or equal to the product of the norms of the A's and phi's, then we will call it contractive. And so in particular, if you take F to be a linear map, then this notion will be contractive. So will be the fact that F is of norm lesser than 1. So something to notice, and that is really important, is that we can define this polycategory without mentioning any notion of tensor product in Banach spaces. So we have a tensor product in vector spaces, but we don't know how to lift it into Banach spaces. And the notion of contractive polylinear map is, I think, something that is easy to define, especially if you compare it to the notion of tensor product in Banach spaces. So from that, we get a forgetful functor. I just forget about the norm. And this forgetful functor won't be a bifibration in general, but it will have all Cartesian lifting of universal polymap. And we saw that it is enough to lift the star representable structure. So this will give us a star representable structure on F-ban1. And we will get, for example, that the tensor product in F-ban1 will be the push forward along the binary map in F-vect, so a map that goes from AB into A tensor B. So we take the push forward, and this will give us a tensor product. And in the other way around, the par will be defined as a pullback along the co-binary map that goes from A tensor B into AB. And if you look, so it's explained in more details in the paper, but if you look at what are pullbacks and push forward in this category for relatively to this functor, when they exist, this gives you that the tensor product is the projective cross norm and the par is the injective cross norm. So as I said, I find it really exciting because it's hard to see when you look at this norm that they are indeed the right norm for the tensor and the par, but this thing put a Star-autonomy structure on F-ban. But they have this universal property. They have this property of being extremal among all the good norms that you can put on the tensor product. And this reflects exactly the fact that this forgetful that they are defined by a push forward and a pull back. And so this gives us a way to find the Star-autonomy structure on finite dimensional Banach spaces by a universal property and just by defining the notion of contractive polymap. Okay, and so to conclude, in this talk, I presented to you a fibrational perspective on models of classical multiplicative linear logic by showing to you that Star-autonomous category correspond to polycategories that are bifibered over one. And using this perspective, I show to you how to lift the Star-autonomous structure along a functor if you have a good notion of polymap on your top category and your functor has enough fibrational property, has enough Cartesian product, Cartesian polymap. Something that we also discussed in the paper and that I don't have enough time to go into is a bunch of polycategorical Grothendieck correspondences. And so in particular, a Grothendieck correspondence between bifibration of polycategories and pseudo-functor into the two polycategory of multivariable adjunction. And using that, so if you specialize this fact to the base polycategory being the terminal polycategory, so we know that bifibration over the terminal polycategory are the same thing as Star-autonomous category. Using the Grothendieck correspondence, so we can get a pseudo-functor. So this will be equivalent to a pseudo-functor that goes from the terminal polycategory into the two polycategory of multivariable adjunction, which is the same thing. So a pseudo-functor out of the terminal polycategory is the same thing as a Frobenius pseudomonoid. And so we get that Star-autonomous category and Frobenius pseudomonoid are in correspondence. And this is something that has been proved and observed by Schulman recently. So some future work that we'll be interested in is first finding other interesting example of polycategories of bifibration, then using polycategories of bifibration to build polarized model for linear logic. And finally, we will be interested in looking more specifically at the case where the base polycategory is compact closed, which is, for example, true for vector spaces. And so thanks for listening to this talk. If you have any question, you can contact us on the Slack channel during the conference. And feel free to go on my website and check the paper and also check this slide if you want to. I will leave you with this nice table that recap all the models of classical multiplicative linear logic that we talk about in this talk. So first, Star-autonomous category where connectives are represented by monadal structure. Then representable polycategory where they are represented by universal objects. Bifibrate polycategory over one where they are represented by push forward and pullbacks. And finally, Frobenius submonoid in the two polycategory of multivariable adjunction, where you get the connective by multiplication and commultiplication. Thank you.